Dimensional analysis allows you to verify the structure of a physics equation before you begin the algebra. By tracking how physical units relate to one another, you can instantly eliminate multiple-choice answers that are mathematically impossible. These three blocks represent mass, length, and time. Every physical phenomenon we measure is built from these primary dimensions. Derived quantities are created when we multiply or divide them. Combine them in specific ratios to map any concept, like force. It is vital to distinguish unit symbols from dimensional symbols. A lowercase m denotes meters, a unit of length. A capital M denotes mass, the physical dimension itself. When you treat physical quantities as building blocks, you gain the ability to dismantle complex problems. Once the base dimensions are identified, the formula's complexity becomes irrelevant. The relationship between a measurement and its unit is expressed as N1U1 equals N2U2. If you switch to a smaller unit, the numerical value must grow by the exact same proportion to keep the physical reality balanced. We can use this to convert a Young's modulus of 12.6 times 10 to the 11 dyne per square centimeter into standard MKS units, newtons per square meter. Instead of memorizing conversion tables, use direct substitution. 1 dyne is 10 to the negative 5 newtons, and 1 centimeter is 10 to the negative 2 meters. By squaring the denominator and multiplying the exponents, the units resolve themselves. This proportional substitution method ensures accuracy across any measurement system. It eliminates the risk of misremembering secondary conversion factors. While you can multiply or divide any dimensions, physics dictates a strict rule for addition. You can only add or subtract terms that share identical physical dimensions. In this kinematic equation, we are adding two terms to find force. Attempting to add units of length to units of time is physically impossible. To reach a final result of force, every term in the sum must also be force. This means that both isolated components, A and B, must possess the exact dimensional formula for force. The trigonometric functions in this formula are dimensionless. Because a sine function represents a ratio of two lengths, the units cancel out, leaving the function and its internal argument with no physical dimensions. To solve for c, we extract the argument ct. In dimensional algebra, dimensionless is represented by the number 1, the identity. Setting ct equal to 1 and rearranging gives us c equals 1 over t, or t to the negative 1. Apply these rules to this exponential equation for pressure. Pause the video here and determine the dimensional formula for alpha. High-level exam equations are governed by these same constraints. If an exponent contains a physical variable, that variable must be balanced by other dimensions, so the final power remains a pure unitless number. We isolate the exponent. Since powers are pure numbers, alpha z over k theta resolves to 1. Substituting known dimensions, z is length, k theta is thermal energy, we multiply energy by length's inverse. Alpha is m1 L1 t negative 2. Identifying alpha simplifies the problem. The dimensionless exponential term doesn't affect the remaining variables' balance. With it removed, we're left with pressure equals alpha over beta. Substituting alpha and pressure's known dimensions yields the final formula for beta. The three rules of dimensional analysis, multiplication and division, are free. Addition and subtraction require matching dimensions. Finally, trigonometric and exponential terms are always dimensionless. Using these rules transforms dimensional analysis into a verification tool. It allows you to catch errors early and ensure your final results are physically consistent.